所以I will lecture in English. But maybe I say a few words in Chinese first. 这个非常谢谢大家对这个课有兴趣。那我想主要我是做一些 random matrix 的计算，然后希望说这个一开始我会讲你的 introduction， 但是差不多 half an hour， 那之后就是一些就像正常上课一样做一些计算。那么所以我希望尽量讲慢一点，然后所以有问题尽量发问就对。Okay. All right. So I will talk about this the random matrix models and so this was I think the starting point was Wigner. And in 1956, I think Wigner was, when I was a student, Wigner was still alive. He was still in the colloquium. And so the question is here a matrix H11? So assume this matrix H is a symmetric or Hermitian. There's also a quaternion case, but I think we'll aim to do the symmetric or Hermitian case, especially the symmetric case. The real symmetric case is actually the main focus. And the reason is because of applications. All right. So 1956, the Wigner want to use random matrix to model this nuclear scattering data. At the time was in nuclear physics, they're trying to do the neutron scattering. And in neutron scattering, they find the neutron scattering pattern cannot be explained by the usual statistical model like Poisson statistics. So we're going to propose to use random matrix as a model. So his idea was if you have many particles interacting with each other, and because you don't know very much about the detail, because the detail are far too complicated. So he think about, so they try to take a matrix which is completely random, and then he want to model the nuclear scattering data. I think I want to say that historically, we're going to start with he started with the so-called random Schrödinger operator. The random Schrödinger operator is the operator H equal to minus Laplacian plus V of X. Now, think about this X. It belongs to a lattice. The reason you want to do a lattice is because it's easier for me to explain what's going on. So this is discrete Laplace operator. And V of X should be V of X omega. So V of X, these are IID random variables. On Z3. This what the idea was, if you want to study the spectrum of this heavy nuclei, so you can think about the one particles, they are intact with many particles. So they have interaction. It's very complicated. So you think about, if you just look at one particles, and this particle, you feel the environment given by all the other particles. So this particle is, so you think about, so to make things easier, you just think about particles in a random environment. You forget about this particle were acting on the rest of the particles. Think about everybody else give you an inference, and this is random. So this is where we're going to start with. And we're going to write the paper. But the question is, he cannot solve this model. So So Wigner cannot solve this model. So then he gave up these models. So he gave up this model and then find another one is even easier. This one says, well, because I can do this problem, then I take a matrix which is completely random. So that's Wigner's idea. Okay. So the question is what are the eigenvalues of H look like? This was the question. And then what we're going to claim is this Wigner's claim, this hypothesis is for any highly correlated system, the spectral statistics are given by random matrices. So this is a grand hypothesis, and of course, you know, the history has many grand hypotheses like this and never been proved, and it's still a useful guide for our understanding of nature. For example, this famous Boltzmann hypothesis. I mean, it's Boltzmann says in equilibrium statistical physics, it's given by ensemble e to the beta h, and h is a Hamiltonian. Now, if you take a physics class, you will start with this is correct, and then you start to think about it. But on the other hand, strictly speaking, this Boltzmann hypothesis has to be proved from Newton mechanics. But of course, nobody ever really proved this completely rigorously. But still, this is very useful. So this is the same. The Wigner's hypothesis is, you say if a system is very complicated, then you can forget about the structural system. Then you just take a random matrix, and then this random matrix will give you the statistical random matrix and this highly correlated system. They are similar. They are actually the same, actually. So what I should say that this is, what you say this is up to symmetry type. Because here, clearly, when you take a real symmetrical Hermitian, they are they are already different. And so now, so I think that the purpose of this lecture is I want to try to answer this question. Of course, not this original question of Wigner, but something much easier and which we still don't quite completely understand. So let me say, mention some applications of random matrices. And this is a reason that there are lots of interest in the random matrices because all these applications. One is the first application is in math physics. The math physics application is very, very funny because this random Schrödinger, this operator is called this random Schrödinger operator. This random Schrödinger operator is used as to model semiconductors. This was a famous work by Anderson. This is Phil Anderson. I don't know if anybody ever been to Phil Anderson's class. I was in his class in statistical physics, and he was he gave a lecture of 1 hour and a half. You know, in Princeton you do this Tuesday, Thursday. So each lecture is 1.5 hours, and then he gave a lecture for 1 hour and a half. He did not really use the blackboard. So his blackboard is just a few lines for 1.5 hours. He just talked, just like a philosopher. And actually, no student understands what he says. Absolutely nothing. So you should go to see his lecture. Anyway, he got the Nobel Prize because he used this is historical, very interesting. Anderson used this random Schrödinger operator to model a semiconductor, but actually this was used by Wigner previously. And the question was, is whether if the eigenvector of H extended, you find this very strange. And the reason is because extended state are connected to extended state is connected to this conductivity. The semiconductor, the conductivity, actually is extended state. Because when I say the eigenvector of H extended, this means if you think about V H of V equal to lambda V, then when you say that it's extended, it just means if you look at eigenvector, this is V of X, this is X. I just want to say that the eigenvectors look like that. I mean, I don't want to give a precise definition. It means when you say it's localized, this is something called localized. This is localized. And this is extended. And then the famous conjecture is if I put a lambda here, sorry, this lambda is this, and this, maybe I shouldn't call this lambda, I call this, give a different name, mu. The famous conjecture is if mu is small, then V is extended. Okay. So this is this question is open. So no single extended state was constructed. Wow, what's fun. So right now, not even a single one. This is very strange. It's you put the potential which are random. You know, you put a lattice, and then you put this. You just put this random. You can also think about it, just randomly put the impurity into semiconductor. Then you want to show that the eigenvector extended. So there's not a single examples. And actually many people try this. Okay, so. And then the second application, localized was proof. So if mu is large, Then it's localized. This was proved by Floric Spencer. And then the second proof by Eisenman. Machanov. I forgot how to spell his name. This was in the night. This was 90 something. I forgot. And I think this was probably the most famous work of Floric. Floric and Spencer. So localized is much easier, but extended is much, much harder. Actually, Bourgain spent lots of time working on this problem and didn't make serious progress on this problem.
So the type of random variable is not important.
It's not important. You can take Gaussian, or you can take Bernoulli. Bernoulli is the hardest one. Okay. So the second example is graph theory. In graph theory, so here I give an example of a D-regular graph. Well, I just first just if you take a graph, it's 1, 2, 3, 4, 5, 6, 7. It doesn't matter what it, and then you start to, suppose you put a graph like that. Like this. So then you can construct a matrix. So here 1 and 2. So you put the 1 here. Okay. Then the 1 and 4. And but you want to make it symmetric, so 1 and 2 and 2 and 1. So this is the adjacency matrices. So graph and the matrix is 1-to-1 correspondence. Okay. So now the question is, so this one, this matrix A and the standard discrete Laplace operator is slightly different. The difference is if you want to make a Laplace operator. So typically, you think about this discrete Laplace on a graph is equal to A minus, depending on how many 1 you have here. Here, for example, in this case, 1, 2, 1, 3. This is 0. So then you put this. It will be minus 2, 1, 0, 1. So the diagonal tells you to count how many 1 is just subtracted. Okay. There are some subtle difference between Laplace operator and A, but roughly speaking, there are many properties they share each other. Okay. Now the question is, so the question is, what are the again, this is the spectral property. Of A. Now, this question is far too difficult because this including almost every single problem you want to ask on random graph. For example, so typically the class we are talking about is a random graph. Now a random graph, there are many classes of random graph. One is this so-called Erdős-Renyi graph. So and the other one is a D-regular graph. And then there are also other class of graphs. And if you remember the lecture given by Fan Jiang, Jin Fanglong. It's actually also about a random graph. So now, so for example, the D-regular graph. D-regular graph is, so this is D-regular graph. D-regular graph means each one, you have lots of neighbors, right? So for example, here's say, there are n-1 neighbors. So you choose random, choose D of them random. Okay. So for example, now here you have a 1, 2, 3, 4, 5, 6, 7. One more. So you have so many edges, but in the real graph, you don't choose this much. You just choose, for example, suppose you think about 3 regular. 3 regular means you take each vertex has 3. Okay, and this one, and then you connect it 2. So this is 3 regular graph. And the Erdős-Rényi is what the Erdős-Rényi graph says is quite similar. It says instead of for each vertex, instead of just choosing 3, what you say is there's a probability to choose D, but this D is again is random. So actually it's much easier. It says now. So roughly speaking, okay. So let me think about it. The Erdős-Rényi graph is the number of edges D is just D, but this D again is random. So this means if you think about this, so you can think about this way. You take a completed graph. And then, so this means all the edges are connected. Then with the probability P, you can choose this edge. And with probability 1 minus P, you don't choose this edge. Just completely randomly choose all these edges. And this is called Erdős-Rényi graph. Erdős-Rényi graph is much easier because what it says is, in terms of matrix, well, the Erdős-Rényi graph says, for example, here this is 1 or 0. So you can say that with probability P, you choose 1. And with probability 1 minus P, you choose 0. So this is the Erdős-Rényi graph. Of course, you have to assume the symmetries. So, but other than symmetry, Erdős-Rényi graph is just independently choose this 1 or 0. Now, see, there's a difference between Erdős-Rényi and D-regular. It's the D-regular. What you have to do is, for example, the D-regular, you know that the total number is 3. So among this number, I choose 3 of them randomly. But the Erdős-Rényi is each one I flip an independent coin, and then I can either choose or either not choose. So Erdős-Rényi is more independent because whether I want to choose this 1 or 0 has nothing to do with my neighbors. So each one is just flip a coin, and then you make a choice. Either it's 1 or it's 0. But on the other hand, for a D-regular graph, there's a constraint because if I assume it's a 3 regular, once I choose 2 of them is 1, then the third one The third one, you can only choose at the most one of them is 1. And then once you choose 3, 1, then I know everything else will be 0. So D-regular graph has correlation because if I know it's 3 regular, if I know this is 1, this is 1, this is 1, I know everything else is 0. So this is serious. On the other hand, for Erdős random, even I know these 3 are 1, everything else is still independent to be 0 or 1. Okay. So the question is the spectral property. There are 2 questions of spectral property. One is about eigenvalues. You look at eigenvalue lambda 1, lambda 2, lambda n, and you want to know the distribution, the probability distribution of this lambda. And the second question is about eigenvector. Now the question is, what can you say about eigenvector? Okay. So it's some property of eigenvector. So I will not write the detail because we also talk about eigenvectors later on, and the reasons is about eigenvector. There's a famous. The reason we are interested in eigenvector for 2 reasons. One is there's something called a quantum unique ergodicity. This is by Rudnick and Sarnak. I forgot how to spell his name. Rudnick, N-I-C-K, I guess, S-A-R-N-A-K. So original conjecture is on a manifold of negative curvature. So the conjecture is if you take a negative curvature and then the eigenfunctions is uniform. It's uniformly distributed. That's angle to infinity. So now you can ask the similar question for the graph. Question is the following. So if you take an eigenvector v of v mu of x of I. Okay. So then you look at this graph v I squared. So now the question is whether this eigen for typical eigenvector value, what it says is this eventually as the graph becomes larger and larger, this will all go to a constant. Well, I should put a 1 to it. So I will explain this in a graph contact. You know, of course, in the beginning, it cannot be complete like a constant. They're some slightly bigger and become slightly smaller, slightly bigger and so on. But as they go to infinity, you become more and more flat. And this is this quantum unique ergodicity. I think there are many people working on these problems in the discrete case also. In the discrete case, including the so there are various work here. So including this Lindenstrass also has some result about this problem. And then finally, the third application is statistics. the statistic applications is if you look at matrix X star X, and where X, of course, X is not symmetric, it's real, but not symmetric. I mean, if you work on statistics, you know that everybody's looking at matrix of this type, X star X, and also there are applications also in the combinatorics of this matrix. So the question is the same. So eigenvalues and eigenvector property. I think that especially the principal eigenvector is in statistics called this is the principal component analysis. The so-called principal component analysis. So the principal component analysis is always just study this matrix and try to understand its largest eigenvector or smallest eigenvector. So, so the reason there are many people in statistics interested in random matrix is because of this connection. Okay, so now so I finished about these applications, and so let's start to do some more serious mathematics works. So first question is Wigner semicircle law. So I want to talk about two things. One is the Wigner semicircle law, and the second one is Wigner universality. Universality of gap distribution. Okay. So I will start with the semicircle law, and then we'll go to the gap distribution. And this is actually rather easy. And the statement of this one is easy, but the proof is difficult. So the semicircle law, this was really proved by Wigner. Okay, so what you do is the following. So you take a matrix H equal to Hij. And this Hij are IID except up to symmetries. It's always up to symmetry, so I will not say it. Okay. Now, suppose we ask the question, how do you know the property of the eigenvalue distribution? And this was a question we're going to try to do it. He did this in the 1950s. So his idea is, so this is called a moment method. Now, there's one thing I should tell the student is, you know, you have done many theory in math, in your math education, but the most theory are completely useless. And if you ask yourself, suppose you are given a problem, what can you compute? There's almost nothing you can compute. And any method cannot compute is useless. And so don't believe any of this abstract theorem says there exists something. It's just all total nonsense. So for example, if you want to you give a random matrix, you want to ask what's the probability distribution of eigenvalues. And then if you learn another theory, say there exists a probability distribution, unique probability distribution for the eigenvalue. It's just, this is another way to solve the problem. So it's quite interesting. So you have to be able to compute. So what we're going to do was he computed trace of h to the 2k. Okay. You know the trace h to the k is if this is 0 because symmetries due to symmetry. So I think here I should say that this hij is this hij. It has the mean is 0. The usual is this and then so let me start define the class. Maybe I should take. So I define the class this hij expectation equals 0 and expectation hij square equal to 1 over n. This is due to normalization. This is normalization. You can think about this as 1. It's just normalized. So let me consider first a class called maybe I should introduce. Oh, sorry. Let me introduce this class. It's Gaussian. So there are two classes. One is the GUE. One is GOE. This is Gaussian Unitary Ensemble. And this is Gaussian orthogonal. Now the Gaussian Unitary Ensemble so this means that hij is equal to, so I should say, okay, the square root of n hij is a standard complex Gaussian. Okay. And the Gaussian orthogonal ensemble is square root n of hij is standard real Gaussian random variables. There are some more detail for the diagonal term, but I will not say now. But so just take this as examples. So in other words, this metric element. Oh, here is small h, a capital H. Okay. So each one is Gaussian. And then what you do is the size, roughly speaking, is Gaussian of size 1 over square root of n. Okay. And now why do I take this? This 1 over square root of n is just normalization. So don't worry about this number. If you change this number, you just stretch the matrix, so it doesn't matter. You will see the reason I put this later on. So just leave it like this. Okay. All right. So now, so let's compute this trace h to the 2k. Okay. So now this trace h to the 2k is h I1 I2 h I2 I3. It's a lot of h, and then I don't know hi something and then I1. Here there's indices, so I didn't write it. And summation over all this I. And then I take expectation. Okay. So now because these random variables are Gaussian, so then you can compute expectation. And then maybe let me try to explain when it's Gaussian, how do you compute expectation? So so this is probability distribution of Gaussian random variables. Okay. And then if I take x squared, I know this is 1. Okay. If I take x to the 4, you know what's the answer? So let's try to see the what? 3? Okay, let me try. $15. Okay. So anyway, so the rule of Gaussian is the following. It's this x to the 6 is 1, 2, 3, 4, 5, 6. Okay. 2, okay. So what you do is you just form pairing. Okay. And then you just count how many ways you can pair them, and the pairing is this number. This is a Gaussian random variable. So Gaussian random variable has this property. It's very nice that you can actually just pair it, and then you count the number of pairing, you will get all these numbers. So there's actually 4. You have 4 of them, and the pairing is this one. You have 3 choices, and there's only 1 choice, so that's why it's 3. Okay, so you can do this Gaussian pairing, and now in this one, what you can do is you start from, say you start from 1 here, and you go to 2. So you have H12, right? Now H12, and then of course you can go to 2, 3, and H23. But at some point you need another pair of 3, 2, or 2, 3 to match it. So this means at some point, so you can, of course you can go to 4, but anyway you have to come back. And then you can go to some other places, but then you have to come back and come back and come back, like that. So this means that in computing this pairing, you have to do something like this. You can go 1, 2, and come back, and then keep on going, come back, and come back. Okay. So this kind of graph. So the number of this pairing, the number of this graph. If you check carefully, this is exactly the Catalan number. So if you are combinatorics, you can go to Wikipedia to search this Catalan number. Catalan number has more than 20 equivalent definitions. And so the number is, so I will not do this. What's this number? Let me see. I'm not very good at this is it's equal to 1 over k plus 1, 2k over k. So I can compute this. And this is, if you compute this, if they are Gaussian, then of course, I should say, I have to mention one thing. It's possible you have a 1, 2. For example, you can 1, 2, and 2, 1, and 1, 2, and 2, 1, right? You can have a H12, H21, H12, H21. But if you look at this case, the combinatoric is much smaller. Because here you do the summation. So let me just give you an example. So you look at this H12, H21, and H13, H31. And compare this one with H12, H21, H12, H21. So here the summation indices is 1, 2, and 3. And when I say 1, 2, this means I1, I2. Okay, so the number, so the combinatorics here, so the number of summation is n cubed because you have 3 variables to sum. But the number of summation here is n squared. So the combinatorics of this one is much bigger. The combinatorics of this one is much smaller. So that's why, of course, this can happen, but then this is the number of terms is much smaller. So this one, this type of term is this term is a leading contribution. In other words, when I say this equal to Catalan number, Ck, this is not completely true. There are some lower order terms. Okay? And the lower order term, one can show that the lower order term, so roughly speaking, this will be equal to Ck1 plus order 1 over n. I think I have to be careful. This, I should normalize by n because otherwise this will be incorrect. Just a second. Oh no, it was correct. Okay, so CK. I think this. Okay, all right. So I probably let me see. I probably made a mistake about, so I have to normalize. I didn't do the normalization carefully, so let me just do one case. I think there's entering some power here. This is because if I compute the, I think there's n here, so I have to divide by n. Sorry, I have to divide by n. So I explain this because if you just compute a trace h squared, this is hi1 I2 hi2 I1, right? Summation of I1 I2 expectation here. So the only possibility is this. Yes. So this is just. Expectation of, we know this expectation, hij squared is 1 over n. So this is equal to 1 over n times summation I1, I2 is n times is n squared. So this is order n. So I have to divide by 1 over n here. Sorry. So there's 1 over n. I mean, this 1 over n is because this. The reason is I start from I1 and I go to I2, right? And then in all these Catalan number calculation, but the trouble is because I also sum over I1. So this means it's not just the number. It's not just the number of this this graph because this I1 can be arbitrary. So this I1 change will give you a factor n, which is not cancel. So that's why. But anyway, you just sit down to do the calculation, you'll find this is correct. So why? So after that, so this was done by Wigner. And then what's the point? Because then, so this implies that, suppose you let semicircle square root x squared minus 4, 1 over, I think 1 over 2 pi, I forgot, 1 over pi or 1 over 2 pi. Well, 1 over 2 pi, okay, 4 minus x squared. So this is the graph of this 4 minus 2 to 2. So this semicircle function. Then you find that the semicircle function x3 2k dx. This is exactly ck. Yes. This is exactly the Catalan number. So this implies that the eigenvalue distribution of this Gaussian, actually GUE is the same, will converge to semicircle. And the reason is because once you can compute the monomial, then you can compute all the polynomial. You can compute all the polynomial, then this implies that you get this convergence. And so the Wigner semicircle law, real statement, is if Hij, these are IID, but not necessarily Gaussian. You don't have to assume the Gaussian. It just has to be IID with mean 0 and the variance 1 over n. And there are some other technical conditions. Then the eigenvalue distribution is converged to semicircle. Okay. So this theorem was proven in the 1950, I mean around this time. Okay, and then we can ask a much more ambitious question. So we're going to ask the following question. So if you have eigenvalues from -2 to 2, and now you ask what's the gap distribution of two eigenvalues. In physics, this is the so-called excitation energy. So he was asking what's the excitation energy probability distributions. And so there was no tool to do this. So eigenvalue statistic of the gap. And then we're going to make a guess. So this is so-called the Wigner surmise. I wish I had a chance to talk to Wigner and ask him why he did this. This is truly amazing story in mathematics. So you want to compute eigenvalue gap distribution, but does anybody knows any method to compute the eigenvalue gap for large matrix? Can you hear me? Okay, I'm sorry. My voice is not very strong, and so the question is, now we learned the mathematics for many years. So you take a matrix, and then a very large matrix you just diagonalize, and then you have eigenvalues, and then if you want to compute the eigenvalue gap, do you know how to do it? There's essentially no way to do it. So actually, I can tell you that Wigner, his knowledge of the random matrix, n by n random matrix, is the same as any first-year freshman, in undergraduate freshman. But he was asking this question, he tried to find the answer. So how did he do it? So this is how he do it. He take a 2 by 2 matrix, okay, and diagonalize it. And this is all you can do, right? You can also do this. And then he find that he diagonalized the 2 by 2 matrix, and then then he found that there would be eigenvalue lambda 1 minus lambda 2 when you compute the probability distribution and so on. And so he tried to guess. He tried to guess that because this is the gap. This is the gap of two eigenvalues. So he think about the function. The gap distribution must look like x e to the minus x squared or whatever. And then he put some constant alpha and beta and so on into this and tried to normalize this distribution. And he came up with a famous Wigner surmise. Okay, maybe let me try to write it down. See if I can find it. Wigner surmise. Or maybe I'll tell you in next lecture. I will find this Wigner surmise. And so we're going to try to do this, and he finds the probability distribution look like this. Then he guessed that this will be correct for large random matrices. He just said this will be correct, and his answer is about 95% to 98% correct, but not completely correct. Okay, so next thing that I want to do is I will try to tell you how to compute the gap distribution for the Gaussian case. So for the Gaussian case, this actually can be computed explicitly. And this was done by Gaussian and Mehta. Now here, actually there's a very interesting story. This was the thesis of Mehta, and I think that many people believe that ideas completely came from Gaussian. So if you find a great thesis advisor, it's very important. And then Gaussian did not work on this field later on. He gave this thesis problem to Mehta, and then he left this field completely. On the other hand, Mehta, based on his whole career on random matrices, his whole career, he wrote a book on random matrices. This thick, it's just everything in his career was working on random matrices. So sometimes to find a good advisor is very important. And okay, so maybe I try to should I start or should I? Okay, it's a good time. Good time to break. Okay, the next. Okay, maybe let me try to say what I'm trying to do. So in the next hour, I will do this computation of. I will spend about half an hour to explain the Gaussian calculation here. This is done by orthogonal polynomial. So I will give you a short introduction of how to use orthogonal polynomial to compute the Gaussian case. And then after that, then we will go to the general Wigner matrices. Okay. And the reason we want to study the general Wigner matrices is because if you want to study the random graph and so on, you have to get out of the Gaussian. So this will be, so next hour will be orthogonal polynomial about a Gaussian case, and then we will start to do the non-Gaussian case. Okay. All right. Thank you. Monotonicity, no. Nobody proved it. This localization, there's a proof of for a large coupling is localized, but for small coupling there's no result, and there's no monotonicity either. So.那我们开始。刚才有个学员问我说，那个为什么 trace 对了，答案就对了？我先解释一下。 Oh, sorry. I'll explain that why the trace is correct then. Because if you compute trace to the h to the 2k, it's equal to the summation lambda j to the 2k over j. So get expectation. Expectation of this. So this is equal to. So suppose you have a polynomial of p of lambda j and summation over j. If you can compute this, then you can compute the lambda j to the 2k. And if you can compute lambda j to the 2k, then you can compute all the polynomial. So what you know is that if you know that this one is equal to polynomial of x, though semicircle of x dx, this of course in the limit. So this minus this goes to 0. So this implies that the probability distribution of lambda j is given by the semicircle law. Okay, if you want to make this more precise, you can define the empirical measure. Empirical measure of is delta of lambda x minus lambda j, summation over j 1 over n. And what you prove is this is p of lambda j is p of x, and this is called omega of x, omega of x dx. And take expectation, then this is minus the semicircle of x, p of x dx is equal to 0. So this implies that this omega x dx will converge to semicircle of x dx. Okay. So this is why you can, once you can compute the moments, then you can compute a polynomial, and from polynomial you can use the polynomial to approximate. So from polynomial you can go to continuous functions, and once you can put all the continuous functions, you know that then this is definition of weak convergence. Okay. So I mean usually I would not very careful about this kind of this weak convergence definition. So because essentially it's you know, the way I'm thinking about this is it's not exactly what's the definition of a weak convergence. It's really in what class of function you can compute expectation, which is the same given by a semicircle. And so you know, this definition, you know, this mathematical definition of weak convergence, this of course is very useful. But at the end, it's in what class of function you can compute expectation so that it's the same, and that's the. All right. So now let's do the Gaussian case calculation. So I start with the GOE, GUE calculations. So now, so before I do this, I introduce a class of invariant ensemble. So invariant ensemble is I define the probability measure e to the minus beta n trace v of h dh. And this dh is equal to product dh. So this is in the case of real. And you can do the same thing with a complex. Now this model is called invariant. It's because if you take a transformation, so consider transformation h go to O O star HO. So this is transformation. So this transformation, so the V of trace V of H is the same as trace V of O star H. And also this transformation leaves this mesh, leaves this DH invariant. So this is why this model called the invariant ensemble is because this measure is invariant. It's invariant under this transformation. Okay. So this implies that this E to the minus beta trace beta n dh this you can integrate out. So we can integrate out the O. In other words, integrate out so that the eigenvalues of this one depends only on eigenvalues. And then there's a calculation. It's probably so there's a preposition says the eigenvalues distribution is given by e to the minus beta n summation v of lambda I 1 to n n times lambda I minus lambda j minus lambda I to the beta product. Okay, maybe. Okay, let me try not to confuse you. So let me erase this beta. Okay. J bigger than I. D lambda 1 to D lambda n. Okay. So and then this beta. Beta equal to 1 for the real symmetric case, and equal to 2 for the Hermitian case, and equal to 4 for the quaternion case. We always just actually quaternion case we don't do very much because in the application it's mostly beta 1 and 2 and so on. So the eigenvalue distribution is explicitly given by this formula. So, so this formula, so let's try to give a proof. Okay. Well, the proof, I will do the proof for beta equal to 1 and the n equal to 2. You know, I follow in the Wigner's idea. You just do a 2 by 2 matrix. So make life easier. So for 2 by 2 matrix, your H, let me see. In a 2 by 2 matrix, your H, it's so you write this x, y, x, z, z, y. You write a symmetric matrix equal to, now you can diagonalize this, cosine theta minus sine theta, cosine theta. And there's eigenvalues, lambda 1, 0, 0, lambda 2, and then this transpose of this matrix, right? You can always write matrix X, Y, Z as this. So then you compute the dx. So you compute dx, dy, dz. This will become d lambda 1, d lambda 2, and d theta. And then there's a Jacobian. So you compute a Jacobian. The Jacobian is quite easy. The Jacobian you find is lambda 1, lambda 2 minus lambda 1. And then there's a function f of theta. Okay. And this is easy because what you do is just you just change your variable formula. It's just 3 variable x, y, z, dx, dy, dz, in terms of lambda 1, lambda 2, and the theta. So you can write the change your variable formula with Jacobian like this. Okay. So then this measure e to the minus n v of h dh, this will go to e to the minus n summation v lambda I. And then you have a d lambda 1 to d lambda n. Okay. And now this lambda 2 minus lambda 1, this is the case of n equal to 2. In general, you will find this lambda j minus lambda I. So in general, you just find the product lambda j minus lambda I, j bigger than I. And then there's f theta, d theta. But this I don't care. This you integrate out, it's just a constant. So it's quite easy. It just change your variable. All you have to check is you will find is lambda 2 minus lambda 1 here. This is just a calculation. It just come out this way. Okay. So in the Hermitian case, you would get this guy to the square, and that's because this variable are complex. So with some simple calculation, you will find that you will actually just become put this become square. So this part it's I think my suggestion is just do a case of n equal to 2 and then convince yourself there's this factor, then you feel pretty happy. Then in general you look like this. And if you have a patient, you can do the n equal to 3. And the general case, it's not hard to do. It's just you need a little bit some property of orthogonal group, but not very much. It's just simple linear algebra calculation. It comes out this way. Okay, so here this preposition. So this means now this v. So this means so from now on. So you study this matrix D mu of lambda like that. Of course, this depends on n. And this beta equal to 1, 2, 4 has a special meaning. So the standard convention is you put the beta here in the problem. But this so instead of look at this, you put a beta here. So this is the standard convention. I don't know what just the real is then this v of x. You take this equal to x squared over 4. And this is the Gauss. This correspond to the GOE case. Okay. All right. So now, you want to study this measure. So we take this, and you want to study e to the minus. Let me take beta equal to 1. So e to the minus n summation lambda I squared over 4 I from 1 to. Sorry. I want to consider case beta equal to 2. Okay. So this becomes a standard Gaussian. It's beta equal to 2. And the product, so I get this delta square. And this factor, this is called delta. This delta is Fundament Determinant. The Fundament Determinant has a very has very special property. So you want to study this measure. I remember that when I was in high school, I saw this determinant calculation. It's actually quite impressive. If you take 1, lambda 1, and lambda 1 to the n minus 1, and 1 lambda 2 to the n minus 1, lambda n to the n minus 1. Okay? You compute this determinant. I don't know, have you ever done this? This will equal to determinant. This determinant of this matrix is equal to product lambda j minus lambda I, j bigger than I. I think there's some plus minus 1, which I don't quite remember. This is quite easy because if lambda 1 equals lambda 2, then this determinant is 0. Any lambda I equals lambda j, the determinant is 0. Okay? And then you compute the degree of the left side and right side is the same, and then it's the same with plus minus sign. Okay, so it's a cute problem. Remember, in high school you always try to actually in high school you always try to do this where n equal to 3, and then it was there was in the old days there's a big emphasis on calculation. So you take a polynomial like this, you put lambda 1 equal to all this put into some numbers, and then try to compute the determinants exactly like that. Okay. All right. So this is Fundament Determinant, and so if I instead I do this, so here I consider polynomial P1, P1 of lambda 1, P2. Let me see, lambda 1. I don't know, P0, P1, Pn minus 1. Lambda n. I think the key idea is this guy. If you compute this determinant, and then you ask this Pn is monic polynomial. By monic polynomial means Pn of x is equal to x to the n. The first coefficient is 1. Then this guy is the same as this. I give it a name. So this determinant, so this is the same as delta. Okay. And the reason is because you see, this one is lambda 1 to n minus 1. So from linear algebra, I know that I can take a linear combination of 1 to lambda 1 to n minus 2 and put everything sum over to here. You will not change the value. So that's why. And then after you make all this, you put, so this is why you can change to any polynomial as long as the leading coefficient is 1. And then you can do the same thing with the next one. And then one by one you can do it. So it goes. So now, so instead of using monic polynomial, you can also say this Pj are orthogonal polynomial. Because the spatial choice is orthogonal polynomial. This orthogonal is with respect to, orthogonal means it's orthogonal with respect to the weight e to the minus nx squared. Lambda j, lambda squared over 2. Okay. So this is why the orthogonal polynomial come into the picture. And then, so I will not do this. So finally, you will see that this measure will be equal to, so I will also do the change of variable, this x equal to square root n of lambda. This is change of variables. So this will imply this d mu of x1 to xn is equal to, when there's some constant, okay, and its determinant psi j xi, this matrix I j from 1 to n, and the square, and dx1 to dxn. And then this, you can multiply out this determinant square, because the square you can take the matrix square, and then if you, this will becomes another constant, prime times determinant kn xi xj, ij from 1 to n, and this kn of xy is equal to summation k from 0 to n minus 1 of psi kx and psi ky. And what is psi k? Psi k is, now I take the psi k of x is equal to pk of x divided by e to the minus x squared over 4, and this is a constant, so I will not write a constant carefully. And pk, now I take the pk because now I have a choice. Pk of x is equal to hk of x, which is equal to minus 1 to the k e to the x squared over 2 times dx to the k of e to the minus x squared over 2. And this is a Hermite polynomial. This pk is a Hermite polynomial. Okay. So I just choose a special class of polynomial which is called a Hermite polynomial, and I use Hermite polynomial, and then I introduce some normalized version. It's called psi k, because this is polynomial, but I want to put a weight. I want to put a weight into this function. So this weight e to the minus x squared over 2, and so then x squared over 2, I distribute x squared over 4 to each one. I call this psi k. And then, so then this measure will become the determinant of psi j xi, which determines square. And then if you multiply this, multiply the determinant, two determinant, then you will get the psi k x, psi k y, and k from 0 to n minus 1 of this one. So at the end, you are studying this measure. So at the end, this is a question you study. So this is called a determinantal process. Determinantal process. In other words, you're studying a probability measure of n particles, x1 to xn, and this probability measure is given by a determinant. And this determinant is given by an orthogonal polynomial, psi k x, psi k y, and k from 0 to n minus 1. So you just study this problem. So, okay. So this was actually this was the work of Golding and Mehta. Okay. And now. Now, I should use the definition, K correlation function. So we have a Pn of x1 to xn. This is probability density. And I assume it's symmetric. Now I want to define the sort of K correlation. It's defined to be Pn x1 to xk and yk plus 1 to yn You integrate. Yes?
In this calculation, is the property that pk are orthogonal with respect to the weight used?
Yes. I think here it's not used, but next step you will use it. You will use it in the next lemma. So here it's not. Here you don't. So far you don't use it. So next one is then you can compute this. So here, what's that? Yes. So there's a preposition. So this P preposition says the following. So this P n k x1 to xk is equal to n minus k factorial over n factorial. Determinant of kn xi xj and I j from 1 to k. This step we use. So this one is quite important actually. This was you see, you have a. I think you probably never thought about any of this. So you have a determinant. You have n by n. You have n by n matrix, right? So, and this is k x1 x1, and so on. If you take this n by n matrix, if you consider its determinant, the size is huge. The size of these objects will be typically is exponential to the n. So the size of determinant of this big matrix is very large. And now, what is the k correlation function? The k correlation function means if you study a problem with a large number of variables, so you have n variables, and even if I tell you the function look like this, it tells you almost nothing because this is still very complicated. It's not computable. Okay, so now suppose I want to know the typical behavior of the two particles here and here. This is just like in statistics, physics, or in statistics says I only care about k of them. So what I want to do is I want to take this k, given this k variable fixed, and then everything else can change. And then I integrate out everything else. So this is roughly speaking, this is the marginal, if you distribution of x1 to xk. So you consider the marginal distribution of the k particles. And so what you do is you fix the k of them. Here I fix the first k of them. And because it's symmetric, I fix the first k of them, or I fix everything. I only have to fix k of them. It can be in any place because it's symmetric. I can move to the front. And then I integrate everything else. Then this is the marginal distribution of k particles. Now the marginal distribution of k particles is amazingly, there's also explicit formula. This explicit formula says you can compute, you can integrate out directly, and then you just, in the beginning, this is kn of xi xj with ij from 1 to n. But when I do the integration of yk plus 1 to yn, you will just reduce this determinant structure to xi xj from ij from 1 to k. And here, when you use here you use this p, this psi function, psi I psi j is equal to delta ij. So you use orthogonality to do this calculation. You can do this. So this I will not do because it's going to take. It's not. I think I would suggest you do the case n equal to 3, and k equal to 2. It's very easy. You can just compute. You compute it, and you find this is correct. Okay. So I will not prove. So this gives you this determinantal formula. And finally, So here, this is the main theorem. The main theorem is the following. It's if you compute this rho n of k, or you fix any energy E. E is any number between -2 and 2, and plus alpha 1 over n times rho semicircle of E, and so on. And divided by 1 over rho semicircle of E to the k. This will converge to determinant. This actually is weak convergence of S alpha I minus alpha j, I j from 1 to k. And S of x is sine x divided by pi x. So this actually is a theorem by Gaussian and Mehta. Probably, I don't know if Gaussian did also an author. In other words, now you take a correlation functions, and or you can think about it as a marginal distribution, and then you just look at the k particles, just look at k of them. Now k of them is x1 to xk. But what I'm trying to say is now if I fix energy E, and then, because remember previously we have eigenvalues, and the eigenvalue distance is 1 over n. Okay? So I want to know the behavior of the eigenvalue at distance 1 over n. So what I do is I compute the correlation functions. I put the k point here. And this k point, each one is E plus alpha over n. So I take a fixed energy E, and this is alpha over n and alpha over n. And this low semicircle of E is because, remember, we have a semicircle law. So there are more eigenvalues here, and they are less here. So you just normalize correctly. So if you normalize correctly, and you take any energy E fixed, and you shift by alpha 1 to alpha k at the scale 1 over n, then you can compute this determinant S alpha I minus alpha j, and this S of x is sine x over pi x. And this is the famous so-called Cosine kernel. And this is the one which appear in the Montgomery's work in the zero distribution of zeta function is this sine kernel. And that's why I was also interested in Montgomery's work, but I don't really know much. So anyway, so this calculation, so this theorem from this formula, so from this formula, to this formula, we need only the asymptotic behavior of Fermi polynomial. Okay. Now, for example, I can give you an example what is really used. It's a Hermite polynomial has a property like, for example, if you know the Hermite polynomial psi m, so you use something like psi 2m of x is equal to minus 1 to the m and n to the 1/4 square root of pi cosine. It's not asymptotic. Cosine of square root n of x and plus order little o. This is follow from the Hermite polynomials go like a cosine and the sine at the end, and this was studied. Oh, what? It's Hermite polynomial defined this way. You put this exponential weight, let's go like a cosine and the sine. And if you use this formula and plug in this determinant formula here, you will see that get this determinant sine x over pi x. So this I will not do. This was just this was really it's just calculation of it's just plug in the property of asymptotic behavior of Hermite polynomial, and then you get this answer. So this was a classical. So this calculation was done in the 1970s. I think this calculation was 1960. Now, so in the 1960s, so people did this calculation. This was fantastic. It's unbelievable that you can compute this. So once you compute this, from here you can get the from this formula you can get the gap distribution. This I will not do. So in statistics, if you know the marginal distribution of k particle for arbitrary k, then you can also get the gap. You can also get the gap, but this is slightly harder, so I will not do it. Now, so the history of random matrix is the following. Then, up to 1970s, up to 1960. So, between 60s and 70s. So they did all this calculation with some more precision. And they are trying to match this with experiment. They're trying to match this prediction. Is with the experiment. But actually, by the end of, close to the end of 1970s, Dyson was very disappointed because the experimental data is not enough. Experimental data is just about something about 50 lines of something like that. The data is not enough to check these statistics. So everybody was so people are very depressed, and then this field completely collapsed. Nobody did it anymore. So that's at the end of 70s. So and also Dyson says by the 1970s they feel that random matrix theory is just beautiful mathematics and has nothing to do with physics. So he was also very disappointed, and then he left, and nobody worked on random matrix anymore. Just and then it goes to 1990. In the 1990, there is a guy, Kitaev. I think he's in my opinion, he's a genius. And so if you look at this calculation I just did on the blackboard, you find that where do I use this Vx is Gaussian. If you look at this calculation, where did I use this Gaussian property? I mean, there are some students want to try where in this whole calculation I use this is a Gaussian. I mean, where is the property of Gaussian used crucially in this whole proof? You see, the Gaussian property used only here. This is the only place I use is a Gaussian. Otherwise, if you take orthogonal polynomial, everything goes through up to this formula is correct. But you cannot take a limit because this Kn of x is given by this summation of orthogonal polynomials. And if I don't know the orthogonal polynomials asymptotic property, I cannot compute to get this formula. So the only place I use Gaussian is this V is a quadratic. It's in this asymptotic formula. So the question is, if I take this as a V, then I can also take orthogonal polynomial with respect to the e to the minus V. And then if all the calculation works out, and then then I will have to know that asymptotic polynomial with respect to the weight e to the minus v of x. Okay. So Kidaev make observations. He said that Riemann-Hilbert problem there's a connection between the Riemann-Hilbert problem and the asymptotic of orthogonal polynomial. Now, this guy is very strange. He worked on quantum gravity, and I have no idea why he came up with this idea to link the asymptotics of orthogonal polynomial to a Riemann-Hilbert problem. And then then this opened up an industry to study the Riemann-Hilbert problem with respect to this weight, and to get an asymptotic of that guy is something similar like this is proof. And then they show that for general class of V, this whole thing works out. So this was the work in the, I think in 1998 to about 2003 or something like that. It's by Itz and Blair Itz. I forgot how to spell his name. Blair, B-L-E-H-E-R. Blair Itz. And also by Percy Dive. Okay. So the whole study of the random matrix just becomes study the random matrix, and based on this idea Riemann-Hilbert problems to study the asymptotics of orthogonal polynomials, and then to study this whole thing. Now this idea this approach has some problem here. One is the problem number one is beta equal to 1 and 4 are much harder. Actually, only partial result was obtained, and also is restricted to invariant ensemble. Because you have to start with ensemble, look like this. If I don't start with this measure, then I cannot study this problem in this way. So now a little bit history. I was actually I was still at Courant at the time. I think around 2000. I was at Courant, and then the slogan at the time was if you want to understand a random matrix, you have to study the Riemann-Hilbert problems. So people pretty soon just completely forget about the problem has a matrix at all. They just completely forget about there's a matrix. They don't even want to talk about there's a matrix. And they just study the asymptotic behavior of orthogonal polynomials. And then it becomes a big industry. And so there are 50 papers published in this direction. They all use Riemann-Hilbert approach. So now, so there's a class which was, so there's a question which is the following. So you take H, okay, and suppose Hij are just independent, RID, but non-Gaussian. Okay. Now, question is, so if this formula for this is called a Wigner ensemble. That's a question. Now, why are you interested in this question? The reason is non-Gaussian.
It's not exponential decay.
No. Gaussian means
Non-Gaussian.
non-Gaussian. Okay. Non-Gaussian means it's not Gaussian.
Gaussian is exponential decay.
No.
Non-Gaussian
Gaussian is this. The Gaussian random variable. If you say x is a Gaussian, if you say Cosine is a Gaussian, this means that the distribution Cosine is a normal distribution of, I don't know, there's a mean alpha and then there's a variance sigma square or something like that. So this means it's probability distribution e to the minus x squared, x minus a minus alpha, and square over 2 sigma squared. The probability density has to be given like this. This is called a Gaussian.
Say this is of the same type as Gaussian.
Sorry?
To work out asymptotic estimates, this is naturally high.
Sorry? 你用中文好了。
我觉得这个就是并没有比，就是 okay. So my question is, I still don't understand what's the contribution of Italian. You just proposed a new way to study systematic way to study
Okay.
Okay. That's the first question. The second question is how far we go from the Gaussian, the original model.
Okay.
Exponential of minus bx.
Okay, I think, okay, now I understand your question. So the problem is the following. So you study this class of measure, right? Now, there's another class. So another class is just Hij. Now this Hij, this is a real random variable. Okay. Real random variable can have a probability distribution of say P of x. This is the probability density of this Hij. Okay. So now here, each metric element are independent. But on the other hand, if you write like this, each metric element is not independent. It's not necessarily independent because you write this as a trace of V of h. So for example, you can write this as, you can think about V of h, h squared plus h to the 4. So this one and this one are not in the same class. The only time that a measure can be written in this way and the metric element, each individual one, are independent is when this V of h is quadratic. So when V of h is ah squared plus bh plus c, then the metric element Hij are independent. Okay. On the other hand, if you write Hij as real random variable with probability distribution P of x, so unless P of x go like e to the minus ax squared minus bx minus c, unless this is correct, then this measure, then this dhi, this p hij dhi product over ij is not going to be written as e to the minus n trace v of h. You cannot, this is just a special class of a metric distribution. And in the case each metric element are IID random variables, then you cannot write a measure like this. This looks a very trivial and simple probability distribution, but this one and this one just not the same. So Kitaev studied this class. His ideas work for this class, and the reason is for this class of measure, you can go through orthogonal polynomial, and his contribution is on the orthogonal polynomial part. But you need the measure to be of this form so the orthogonal polynomial is useful. So in other words, once you keep in mind this idea of orthogonal polynomial is useful only for this class. But for this class, it's just there's just nothing you can do. Okay. Now, I was very interested in this problem because they always talk about this is a case they can't do, because once you do the Riemann-Hilbert problem, this is a class they can't do. So, and this class is particularly interesting is because if you think about central limit theorem in probability theory, the central limit theorem says the central limit says if you take IID random variables, you take n of them divided by square root of n. This goes to Gaussian, normal. Wow, Gaussian. Okay, doesn't matter. I mean, this Gaussian and normal is quite funny. People in probability always call it Gaussian. People in statistics always say it's normal. So you can tell whether it's working on statistics or working on probability just by. So this is a Gaussian. But of course, this x1 to xn is a Gaussian. You sum together, divide square root is a Gaussian. On the other hand, this is IID random variable, it still go to Gaussian. And then the question we are asking here, this is a metric version of central limit theorem. Because what we are saying is here, this is GOE or GUE. And this is Wigner matrix. This is the class of Wigner. And then you want to say that the correlation functions of the Wigner and the Gaussian, they are the same. So in a way, what you're asking is something similar to the central limit theorem, but in the case of matrix. And this is what's the. So that's why. And it's a little bit propaganda. You see, the whole probability theory, and until about 20, 30 years ago, everything is centered around independence and the Gaussian. So this is a class which is not independent and which is non-Gaussian. But on the other hand, you can compute, and so that's why this class of distribution is important, and that's why we are trying to establish something similar to the central limit theorem to this class of random variables. So, and now, and the other reason that this class is interesting is because this class will include all this graphic, all this combinatorics, all this graph theory, and so on. It's already in this class. You will never get into this class. So any combinatorics application has to come from here, and that's why that's why we spend so much energy to try to understand this problem. And especially we want to know that when this guy chooses 1 or 0, in this Hij belong to 0 or 1 case, this is the class we are particularly interested in. Okay? So I hope I answered your question. Yes? Well, okay. All right. So let me continue.可以啊，你就问啊。嗯哼。No. No, I think. Okay, the question was if because I take Hij in the IID case, and I think your question is in the IID case, this is just a perturbation of a Gaussian, but this is not true because if you think about this, if I so if you think about the Bernoulli case, this Hij belongs to 0, 1. And actually, it's up to normalization. It's good in Hij belongs to 0 or 1. Okay. So then the probability distribution is is delta 1, is delta x minus 1 of p and plus delta x minus 0 of 1 minus p. And then you take this as, you put this as delta hij minus 1 p plus delta hij minus 0 of 1 minus p. And you take this one, you take a product I less than j. This measure, you will never be able to approximate by something of this form. It's just not possible. And the second question, I think much more serious, is if you take this product, polynomial hij, dhij, take it like that. And if you do a transformation, h goes to O star ho, then this measure will not be invariant. So this measure, omega, is not invariant under this transformation. So these two classes are completely separate. This class is called a non-invariant class. Okay. So maybe I will continue and we can discuss this after the talk. Okay. So all right. Now, so for the question. So for the Wigner matrices, the Wigner matrix means expectation hij is 0 and expectation hij squared equal to 1 over n. And of course, you also require expectation hij to the k times the square root of n to the k is less than constant ck. So this is some higher moment control conditions. And now, the only theorem we have is Wigner semicircle law. The Wigner semicircle law says the eigenvalue distribution is given by that. The density of the eigenvalue is more here and is less here. Okay. Now, so we want to ask a question, the following. So I will study or consider this question of Stiger transform. The Stiger transform of m of z is equal to 1 over n summation of alpha so if you have eigenvalues lambda 1 to lambda n, then you consider the z is a complex. This is called a Stiger transform. This is Stiger transform of the measure of the empirical measures. Summation delta x minus lambda alpha. Okay. Now, the Stiger transform can also be written as 1 over n trace of Green function. And the Green function is h minus z. This is called a Green function. So what we know is this mn of z. This mn of z. Oh, by the way, I have this lecture. I have this my class lecture, and this is a lecture I gave at Harvard, and it's about 130 pages. But then I didn't completely correct all the details. So there are still some comments I left. I mean, it's I wrote this with Lars Erdős, so there are a few pages. It's not complete. I can give it to you, but you should not distribute because there are still comments. They are still incomplete, and I'm following this note, and you can take a look. So what? G is this. This is a definition. So in my training, the green function is almost always the quantity you want to study. And so now the mn of z will converge to MSC of z. The MSC of z is z minus x, the semicircle of x dx. This means if this x variable is given by the semicircle law, I call it a semicircle. But because the empirical measure will converge to the semicircle law, so I know that mn of z is going to be MSC of z, which is this is semicircle. Now, so this is a fact. Because this semicircle is explicitly computable, so the MSC of z it actually can be computed. It's minus z plus square root of z squared minus 4 divided by 2. And this is the solution. It's a solution to the equation m plus z equals 0. Okay? So this we know. Now, so this convergence actually is just what we know is just weak convergence. Okay. So now the next thing is we want to study. The main key question is suppose m of e plus I. There's an n here. Okay. Now we want to study the convergence of this one this is always the z. We want to say that this one minus this one is small when eta is of the size of 1 over n to the 1 epsilon, the 1 minus epsilon. So this is our goal. So this was something we study. We started this problem in something like I think it's 2007. So let me explain the idea. So if you look at this guy, you just look at the imaginary part. It's 1 over n summation. Now this imaginary part is e minus lambda alpha square plus eta square of eta, right? So this function is the imaginary part of x plus I alpha. Imagine by x plus I alpha, it looks like a delta functions like this, and the width is eta. The width is eta, and the height is eta minus 1. I mean, this is correct because this is the imaginary part x plus I eta is x squared plus eta squared over eta. So when x is of order eta, this is 1 over eta. And then this width is width eta. So this quantity means you have this eigenvalue lambda 1 to lambda n, okay? And now each one you fatten up by the size eta. Each one you fatten up by size eta. And then you take an average. Okay. So this means, of course, when I set eta equals 0, if I take eta equals 0, then I get delta function. Okay. So it's just a modified delta function, and the scale of modification is size eta. All right. So now, so this quantity, imaginary part of Z, is this is if you look at this, so this energy E. Roughly speaking, you take energy E, and then you take a window eta. Okay. Then this quantity roughly says the number, the density of number of particles. I mean, I call eigenvalue particles at E in the window. Okay, you agree? You study the size of时间到了. Oh, I'm sorry. Okay, I guess. All right, sorry. So I think I should stop. Okay, so next time I will state the theorem about this, and I will start to do the Dyson-Brownian motion next time. So I hope I can finish Dyson-Brownian motion next time, and if they are interested, then I can continue to say more recent work. We are using more PDE method to do this problem. Okay. All right.